Time domain specification of second order system. Now let us consider the time specification. Now in this diagram we have MP is the peak or the maximum peak. Then we have TD, which is the time delay. TD is defined as the 50% of the first attempt to reach its final value. Next we have TP, that is the peak value, that is the first attempt to reach the maximum value. Next we have TS, it is the settling time after the transient has died out. Next we have the tolerance. The tolerance has 2% or 5% of the steady state value. Next, the time constant is given by 1 by zeta omega n. This we have derived in the previous session. Now, delay time is defined as the time required for the response to reach 50% of the final value in the first time. The rise time, it is the time required for the response to rise from 10% to 90% of its final value for overdamped system, 0 to 100% for the underdamped system. And this is the equation which is useful for understanding the time specification. Now let response reaches 100% of the desired value. Put C of t is equal to 1, which indicates 1 indicates 100%. Then what we are left out? We are left out with this equation, that is e power minus zeta omega nt divided by root 1 minus zeta square sine omega dt plus phi. I can write this whole thing as omega d. Now if I equate this into 0, I know that e power minus zeta omega nt cannot be equal to 0 because it is not under natural frequency. So what is the other term we have? The other term we have is sine omega dt plus 5 is equal to 0. So I can put n value as 1. So what we get? We get the equation as omega n root of 1 minus zeta square tr plus 5 is equal to pi. So the final equation that we get is tr is equal to pi minus tan inverse root of 1 minus zeta square divided by zeta, the whole divided by omega n root of 1 minus zeta square. Peak time. The peak time is the time required for the response to reach the first peak of the time response or the first peak overshoot. Again, to find the peak overshoot, I need to differentiate so that I will know the change in the system. So dc of t divided by dt is equal to 0. So the equation that we get is this when we differentiate. Again, when we equate to 0, I know that e power minus zeta omega nt will not be equal to 0. So we consider the other terms. So when we consider the other terms, I know that sine phi is root 1 minus zeta square, cos phi is zeta. How do we know that? We know that from the triangle, that is, if I write this as phi, I know that this is root 1 minus zeta square, this is zeta, and this is 1. So when we solve this in terms of tan phi, I know that uh, tan omega n root 1 minus zeta square into t plus phi is equal to n phi. Omega n root 1 minus zeta square into tp is equal to n phi. When n is equal to 1, 2, 3, the peak time of the first overshoot we get when n is equal to 1. That is pi divided by omega n root of 1 minus zeta square, or I can write this as pi divided by omega d. So if I want second overshoot, I'll substitute n is equal to 2. Then we get it as 2 pi divided by omega d, and goes on. Maximum overshoot. To find the maximum overshoot, we'll take t is equal to Tp. The maximum peak exists when pi by first overshoot exists when pi by omega d. So when we substitute these values in the equation, in the above equation, we get percentage MP as e power pi zeta divided by root 1 minus zeta square into 100. The last part is the settling time. The settling time is defined as the time required for the transient response to reach and stay within the prescribed percentage error, that is 2% or 5%. So the time consumed in exponential decay up to 98% of the input. The settling time for the second order system is approximately 4 times the time constant. That's why I can write Ts as 4 times T, and I know that this capital T is nothing but 1 divided by zeta omega n. Since it takes 4 times, it is 4 divided by zeta omega n. Whereas in the first order system, it takes 5 times. The steady state error, it is the difference between the actual output and the desired output, as time t tends to be infinity. Now let us consider an example of open loop transfer function of a servo system. G of s is equal to 10 divided by s plus 2 into s plus 5. Determine the damping ratio, undamped natural frequency of oscillations. What is the percentage overshoot of the response to a unit step? So first thing is we consider the forward gain, that is G of s is equal to 10 divided by s plus 2 into s plus 5. So H of s is equal to 1. So characteristic equation is given by 1 plus G of s into H. So we get the characteristic equation as s square 7s plus 20 is equal to 0. Since it is in the standard format, I can easily compare with s square plus 2 zeta omega ns plus omega n square. So omega n square is equal to 20, 2 zeta omega n is equal to 7. So omega n is 4.472 rad per second and zeta is 0.7826. Now as you can observe, the peak overshoot formula is MP is equal to e power minus pi zeta divided by root 1 minus zeta square. Understand this, zeta is directly linked with peak overshoot. So if I know the zeta value, I can easily find the peak overshoot. So it is 1.92%. Now let us consider another example with K gain. So a feedback system is described by a following transfer function. G of s is equal to 12 divided by s square plus 4s plus 16, and the feedback is Ks. The damping factor of the system is 0.8, that means which is less than 1, that is underdamped. Determine the overshoot of the system and value of k. So if I find the total transfer function of the system, I know that C of s divided by R of s is equal to G of s divided by 1 plus G of s into H of s. So C of s divided by R of s is equal to 16 divided by s square plus 4 plus 16k into s plus 16. Understand this, the characteristic equation is not multiplied with unit step. It is other than the unit step. So if you multiply again an s function, the whole system will change. The output response will change. So the characteristic equation is s square plus 4 plus 16k into s plus 16. Now this is a second order system and it is in the form of standard equation. S square plus 2 zeta omega ns plus omega n square. When I compare with the standard equation, I get omega n square as 16. So omega n is 4 rad per second. 2 zeta omega n is equal to 4 plus 16k. There are two unknowns, zeta and k value. So the zeta value they have given as underdamped, that is 0.8. So k value is 0.15. So again, the peak value is MP is equal to 1.5%. So let us take another example. The open loop transfer function of a unit feedback control system is given by k divided by s into 1 plus st. By the factor, the amplifier gain k should be multiplied so that the damping ratio is increased from 0.3 to 0.9%. So first thing, find the transfer function and find the characteristic equation. The characteristic equation we get is s square plus s by t plus k divided by t. So since it is in equivalent with the standard equation, I can easily compare it. So I get omega n is equal to root k by t. Zeta I get is 1 by 2 root kt. So the given value is zeta should vary from 0.3 to 0.9. So I have zeta 1 is equal to 1 divided by 2 root k1 into t. Zeta 2 is equal to 1 divided by 2 root k2 into t. So the value I get is k1 is equal to 9 times k2. Hence the gain k1 at which zeta is equal to 0.3 should be multiplied by 1 divided by 9 to increase the damping ratio from 0.3 to 0.9.